Welcome. This chud Euler guy wanted me to check this so-called number that he found and check the convergence so that he basically consults me with all of his maths questions. I'm like his numbers guy. And that number is gonna be the limit of n approaching infinity of this so-called harmonic series minus the natural logarithm of x. So he calls it the macaroni constant, and it's just stupid. I'm gonna call it the Mascheroni constant, and it's basically the limiting difference of two divergent series. We know the harmonic series is gonna look like 1/n. So it's like 1 + 1/2 plus plus blah blah blah, so on and so forth. And basically, the series is divergent, and same with the natural logarithm of n. So both of these grow really, really slowly. Like genuinely, just imagine dexter running, right? So we need to check if it actually converges. So our definition of the harmonic series, as I was just saying, is nothing but the sum running from k equals 1 to n of 1 over k. And so we are going to treat this as like a sequence. Like if let's say we look at some gamma n's, this is going to be hn minus ln of n. And at the limit of n approaching infinity, it's going to be gamma. So to show that this converges, we want to show it's strictly decreasing. In other words, each member is going to be less than the next member. So like if this first, let's say this is the gamma n term, this one would be gamma n plus 1. That's what we want to show, right? The next term is going to be smaller than the last term, so it strictly decreases. Or, in mathematical words, gamma of n plus 1 is less than gamma of n. That's what we want to show. So we want to look at some gamma of n, right? Like gamma n minus gamma n minus 1. And so we're just going to plug in our definition of gamma n. We've just defined what gamma n is, hn minus ln of n. So for this, it's going to be hn minus ln of n minus hn minus 1 plus, because two minuses make a plus, ln of n minus 1. We know this term has a partial sum definition. And so all of these terms here are going to be within this partial sum. This is a partial sum. Okay? And so because this is a member, all of these terms are going to be in it. And this sum goes to 1 over n. So all of the stuff in here is just going to cancel with the stuff in here. And we're just going to be left with 1 over n, basically. So we also have our log rules. So for ln of a minus b, it's essentially just going to be what? For ln a minus ln b, it's essentially just going to be ln of a over b. So the ln terms are just going to become ln of n minus 1 all over n. And we can change the fraction, just make it a little bit nicer. This is going to be ln of n over n minus 1 over n, or just ln of 1 minus 1 over n. Great. Cool. So what do we have? Add a new page here. What do we have? I didn't even need a new page. It's lying to me. We have 1 over n plus ln of 1 minus 1 over n. So let's look at my friend Taylor. He came up with this series called the Taylor series. And for ln of 1 plus x, it's basically going to be the sum running from k equals 1 to infinity of 1 minus 1 over n. What am I saying? Genuinely, what am I saying? It's just not though, is it? It's going to be minus 1. Sorry, I'm getting confused here. To the k plus 1 power all over k times x to the k power. And if we plug in -1 over n, we are going to get the sum running from k equals 1 to infinity of -1 to the k plus 1 power all over k times -1 over n to the kth power. Brilliant. So now we can break this up to -1 to the kth power times 1 over n to the k. Then we have -1 to the k times this -1, giving us -1 to the 2kth power, and any negative -1 to the 2kth power to any even power is going to be +1. So all that's really left is the negative. So in other words, it's just going to be the negative. K equals 1 to infinity of 1 over k times 1 over n to the kth. And this is good, because if we plug this in, then we're going to have 1 over n minus the sum running from k equals 1 to infinity. I wonder how many times I've said that. Of 1 over k times 1 over n to the k power. Cool. So what's the first member of this series? Or plug the numbers in. What are we going to get? We're just going to get 1 over n to the kth power of 1, so 1 over n. In other words, we have 1 over n minus 1 over n, and so the first member cancels. So this is just going to leave us with it from 2. So we've actually got the sum from k equals 2 minus, there should be, to infinity of 1 over k times 1 over n to the k power. Now this whole sum is strictly greater than 0. But minus n when n is positive is going to be strictly less than 0, right? So basically, gamma of n is going to be gamma of n minus gamma of n minus 1 is going to be strictly less than 0. So gamma of n is less than gamma of n minus 1. And so if we add on n plus 1 to both sides, we have gamma of n plus 1 is strictly less than gamma of n, which is what we wanted to show. So we have shown that the sequence is decreasing, basically. And we can find another bound if we look at the first term in the sequence. So that's what we're going to do now. Let's look at gamma of 1. This is going to be h1 minus ln of 1. What is ln of 1? 0. What is h of 1? Well, it's going to be nothing but 1. So our gamma in the limit of n approaching infinity is strictly less than 1. Cool. So we found an upper bound, but we still don't know if our gamma converges to a certain value. So let's find the lower bound. Let's look at the natural log as an integral. So that's what we're going to do. We're going to have a look at the natural log, and we can define this, I hope you agree, as nothing but the sum from 1e to n of dt over t, because this will just give us our natural log, the natural log of n, and then the natural log of 1 is just 0, so we just have the natural log of n. And we can find all the partial integrals that exist, and we can break this sum up. So, like, in other words, if you have the integral from a to c, we can call this the integral from a to b plus the integral from b to c, right? So we can break this up. So for our case, it's going to be that ln n equals the integral from 1 to 2 of dt over t plus the integral from 2 to 3 of dt over t plus integral from n minus 1 to n of dt over t. Yes. And this is nothing but a finite sum from k to n minus 1. So we can write that out. It's going to be the sum from, let me think about this, k equals 1 to n minus 1 of the integral from k to the k plus 1. Yes. of dt over t. Cool. And we want to show those partial integrals are bounded so that the integral k to the k plus 1 of dt over t is just going to be ln of k plus 1 minus ln of k. You agree? Plug the numbers in. And that is nothing but ln to the k plus 1 over k, or just ln of 1 plus 1 over k. Cool. And let's consider this argument, right? Let's have a look at 1 plus 1 over k. Now, we have a very similar definition for the Taylor expansion at e to the x. So if we have a look at e to the x, this is nothing but the sum running from k 0 to infinity of x to the k over k factorial. And so e to the x here is less than 1 plus x, and it's positive, so it's strictly greater than 1. For our case, we're starting at 1, so we can just say that e to the x is greater than 1 plus x in terms of for us. So essentially, 1 plus 1 over k is going to be less than e to the 1 over k. And this is a nice approximation. So our ln that we looked at cancels with, and we're just going to be left with that ln of 1 plus 1 over k is strictly less than 1 over k. Cool. And we can do this for the partial sums in our integrals, right? So I'll rewrite it out, it's fine. The sum from k equals 1 to n minus 1 of the integral from n k should be shown k to the k plus 1 of dt over t is going to be strictly less than, well, it's going to be the sum running from k equals 1 to n minus 1 of 1 over k. And this is nothing but the harmonic series of hn minus 1. So meaning that overall, we have that ln of n is strictly less than the harmonic series for n minus 1 for our term. And in our chud Larpers, his Euler-Mascheroni constant that we have, we are going to say that gamma of n is going to be the harmonic series minus the natural log of n. And here we have negatives in, so we're going to multiply both sides by minus 1. And we will get that minus hn minus 1 is going to be less than minus ln of n. And so we have hn minus hn minus 1 is less than hn minus ln of n. Right? And this right here is nothing but gamma n. And what is hn minus hn of 1? Well, that's just going to be 1 over n. So what we have is we know that hn is just 1, then 1 over 2, then 1 over 3, etc. And all of these are strictly greater than 0. So what we can say is that 0 is going to be less than 1 over n, which is less than gamma of n, which is less than equal to 1. And if we let n go to infinity for 1 over n, well, what's going to happen? We're just going to be left with that 0 in the limit I'm talking about here is less than gamma, which is less than 1. And gamma is something like 0.577215. And so, yeah, we did it. That's a nice little proof of convergence here for what we've just done, is we've shown that it was decreasing, and then we've shown that it has those bounds that we found. And so yeah, this has been a nice little proof of convergence for my friend Euler. He wanted us to solve it. So yeah, make sure to like and subscribe if you want to be better at maths than Dexter. Got to be better than him.